All right, let's get started. So it's a pleasure to welcome our speaker today. It's Marco Linton from the University of Warwick, and he's going to tell us something about hyperbolicity of certain one-relator groups.
Thank you very much, and thank you very much for inviting me to talk here. So today I'm going to talk about hyperbolicity of certain one-relator groups. All the results I'm going to present today are currently in my paper on the archive, one-relator hierarchies. And yeah, so let's get to it. So please let me know at any point if you have any questions, if I'm going too fast or too slow or anything. I'm happy to adapt. So this is the structure of the talk. So first I'm going to just introduce one-relator groups briefly. I'm going to give some examples, some which you may know, some which you may not. Then I'm going to discuss this quantity primitivity rank. I'm going to talk about some recent results, connecting the primitivity rank with some properties of one-relator groups. Then I'm going to discuss some the main results of my thesis, which are going to be building on this. And then that'll be the first half of the talk. And then the second half, I'll sort of discuss how one proves these results. So I'll talk about hierarchies of one-relator groups. These are essentially, yeah, if you know of the Magnus hierarchy, then essentially building on that. And I'll discuss different types of hierarchies and equivalences and stuff like that. And then finally, I'll talk about this negative emergence property and how that connects to one-relator groups and the whole story. Okay, so let's first start by defining what a one-relator group is. I'm sure it makes sense from the definition, from the name. So a one-relator group is a group with a presentation with a single defining relation, but I just want to have it so we start well. Okay, so that's what a one-relator group is. Let's go through some examples. So free groups, okay, we can just take the relation to be an element of the generating set. So that is just quotient by normal closure of this guy is going to be a free group on one fewer generators. Surface groups, another well-known class of one-relator groups. So we have the orientable ones here and the non-orientable ones here. Another class of well-known one-relator groups are bounce-like solitar groups. So these are parameterized by two integers m and n, and we have two generators. The B generator conjugates the power of A to another power of A. So yeah, these are quite interesting groups. They contain non-residually finite groups, non-Hopfian groups. They are an obstruction to hyperbolicity. So in particular, in this talk, we'll be interested in finding or not finding these subgroups in one-relator groups. And then, so these are sort of, yeah. And then we can talk about some slightly more complicated examples. So these groups are known as bounce-like Gerson groups. These are H-n extensions of bounce-like solitar groups. So if we sort of bracket these guys and these guys, we can see that it's sort of conjugating power of A to another power of A by this element, so not by B. So these were, yeah, these are sort of one step up from a bounce-like solitar group, and they're pretty nasty groups. They have Dane function, well, let's say G12 as Dane function, which looks like some iterated tower of exponentials. And this is log base 2 of n. This is proven by, I think, Platonov, I believe. So yeah, the Dane function can be pretty nasty. Already the bounce-like solitar groups have exponential Dane function, but then if you take a H-n extension of that, then you can get something even more horrible. Other examples which I quite like are these groups which are introduced by Garden in his thesis. So these groups are parameterized by these two integers m and n. Okay, we can't really say much just by looking at it, but these are virtually what are known as snowflake groups, which were these snowflake groups were introduced by Brady and Bridson. And they show that these groups have essentially polynomial Dane function, and the polynomial exponent can be sort of, well, the closure of all these exponents is essentially everything between 2 and 2 upwards. So the sort of exponents are like dense in the reals from 2 upwards. And yeah, they're virtually these groups. So the sort of Dane functions of one-related groups can be quite vast. So it's not, yeah. And yeah, other examples are para-free groups. So, well, many para-free groups are one-related groups. These were groups introduced by Bouncelag in the 60s. I'll say a little bit more about these later on, but I've just sort of left an example of a family of para-free groups. So these words probably should be in the derived subgroup actually. So it's just, yeah, okay, I don't need to write that. So they're in the derived subgroup of on these generators here, and same here. So this is known as a Bouncelag double, and these are para-free. So I'll say, yeah, I'll say more on what para-free groups are a little bit later on in the talk. But the point is that there's a big variety of one-related groups which display a lot of different properties. So yeah, the theory is quite rich and quite old. Okay, but I want to talk about some more recent work. So first we need to define what the primitivity or imprimitivity rank of an element of a free group is. I put this in brackets because I think some authors use imprimitivity rank or primitivity rank to mean the same thing. So if you're someone who likes to think of it as imprimitivity rank, then I will be talking about the same thing. So what is it? Then the imprimitivity rank of an element W in a free group is essentially the smallest rank of a subgroup containing your word W as an imprimitive element in K. Imprimitive meaning just that it's not a member of a basis or a free basis of your free group. And this can take values from 0 up to infinity. But yeah, it'll be bounded above by the size of the generating sets unless your word is primitive, in which case it'll be infinite. So yeah, first let's say some remarks. So okay, if your word is a proper power, so with n greater than or equals 2, then your primitivity rank is going to be 1, because no power, well, yeah, the power is the power is imprimitive in the subgroup generated by the root, right? So yeah, so that's an easy case which you can sort of compute just very hands-on. Check if it's a power. If it is, then your primitivity rank is 1. If not, then it's not. The primitivity rank is infinite if and only if your element is a primitive element of your free group. And again, this you can use Whitehead's algorithm. You can to tell whether it's primitive element, and therefore determine if this is infinite. But more generally, you can compute the primitivity rank of your elements anyway. So this algorithm was given by Couder in 2011 when he introduced this quantity. And a year later, he also showed that generically, so as you take sets of words larger and larger size in the free group, generically the primitivity rank of these guys are going to be equal to the size of your generating set. Okay, And just as another simple example, so take this word W, okay? If you stare at it a little bit, you'll see that it has primitivity rank 2, because this word is not primitive in the subgroup generated by these two generators. So if you sort of rewrite this, you'll see it looks like a bounce-like solitar relation in this subgroup. So you have this a squared, b squared, c squared, and you've got this b here, and then another, got the inverse of this guy, conjugates, so it conjugates this b squared to that b cubed. Okay. Well, so what does this have to do with one-related groups? Well, we didn't know until 4 years ago when Lars Lauder and Henry Wilton came along and proved this fantastic theorem. So they showed that given a free group and an element W in your free group, the quotients, so the one-related group with presentation, generators of F and relation W, is primitivity rank of W minus 1 free. So that means that every subgroup generated by this many elements of your one-related group is a free group. So this sort of echoes a little bit the Magnus Freiheitssatz. And in fact, while it's not really a strict generalization, if you have full primitivity rank, so your primitivity rank is equal to the size of the generating set, then you recover the Freiheitssatz, right? And I mean, moreover, they also reprove the Freiheitssatz in their paper. It's a very nice proof, but not using this theorem. Okay, so what does this tell us? Well, it tells us that we have some strong connection between the subgroups of our one-related groups and this sort of property of the defining relation in the underlying free group, which is very nice. So, for example, what we can see from this theorem directly is, well, suppose we have primitivity rank 2 or more, then the quotient is going to be 1 free by this theorem. And what does 1 free mean? Well, it's the same as being torsion free. So this sort of recovers another theorem due to Crass, Magnus, and Solitar, that one-related groups have torsion if and only if their relation is a proper power. So if and only if your primitivity rank is equal to 1. Okay, now another thing we get from this is, well, if the primitivity rank is greater than or equal to 3, then you don't contain any bounce-like Solitar groups, because you are, because every 2 generated subgroup is free. And well, there's this big conjecture of, there are several different variations of these conjectures, which sort of essentially say that really we should expect that a group without bounce-like Solitar subgroups should be hyperbolic. Now, this was disproved in general quite recently, but it's still open for many classes of groups, one of which is one-related groups. So this sort of discovery of Lauder and Wilton pushed them to sort of conjecture that 2 free one-related groups should be hyperbolic. I mean, if this conjecture were false, then, well, yeah, we'd be in trouble. We'd have some 2-dimensional groups which, all their 2 generated subgroups are free, so no bounce-like Solitar groups, but it's not hyperbolic. So really, this conjecture, we really hope is true. And, well, maybe I'm going to ruin the punchline, but I think I've said in my abstract anyway, this turns out to be true. So I think before I state the main terms, I wanted to sort of go through some of the sort of other results which sort of connect the primitivity rank of the relation with properties of the quotient group, of the one-related group. So as I already mentioned, having torsion is equivalent to having primitivity rank 1, having a relation with primitivity rank 1. So this was proved in 1960 by, well, this is Carras, Magnus, and Solitar, using completely different methods. And so, so 1, you have torsion, elements of finite order, and 2, no, because you're 1 free, 3, again, also 1 free. Okay, next property, hyperbolic. So, okay, we already said that here it's conjectured. What about primitivity rank 1? Well, this was proved by Newman in 1968. The theorem is known as the spelling theorem. Now, obviously, hyperbolic groups hadn't been defined at that point, but what Newman does prove in this theorem is that one-related groups with torsion, their one-related presentation is a Dane presentation for the group. So then, I mean, hyperbolic groups are, pretty much the groups which have admit Dane presentations. So we get this result that one-related groups with torsion are hyperbolic. And moreover, we have like a very direct way of solving the word problem very fast. Okay, so what about primitivity rank 2? What happens? Well, no, as I said, these bounce-like Solitar groups are like Poisson subgroups for hyperbolicity. So since these guys have primitivity rank 2, these relations have primitivity rank 2, means that we can't hope for any hyperbolicity results here. Then, okay, we have the conjecture of Lauder and Wilton. That's if you have primitivity rank 3 or greater, then you are hyperbolic. Next property, so residual finiteness. This was conjectured. So I'm using just the letters because I couldn't figure out how to fit the whole names. So I'll just say the name. So this is a conjecture of Baumslag, Gilbert Baumslag, from the 60s. So he conjectured that one-related groups with torsion are residually finite. And many years later, Danny Wise came along and proved this is indeed true, that one-related groups with torsion are residually finite. Then again, for primitivity rank 2, this is false. They're not residually finite because we have these, again, Poisson subgroups, bounce-like Solitar. Well, so this guy is residually finite, but this guy is not. So that sort of kills any ideas there. What about greater than or equal to 3? Well, there's not really, I mean, there's not a conjecture or anything here, but so I just left the question mark for now. Another property which is quite interesting is coherence. So this is Baumslag. This again is Baumslag, conjectured in 1974 that all one-related groups are coherent. Coherence means that all your finitely generated subgroups are finitely presented. And well, this was confirmed for primitivity rank 1 by Lauder and Wilton and Danny Wise at around the same time. But then for primitivity rank 2, it's completely open. And finally, for primitivity rank 3 or greater, this was confirmed by another paper of Lauder and Wilton on one-related groups. So that's sort of the picture until, let's say, last year. And today I wanted to talk to you about my sort of contribution to this table. So what have I proven? Let's see, main results. Perhaps this is a good time to stop and ask if there are any questions. If not, I will carry on. Okay.
Just a moment. So having a permittivity rank 1 is the same thing as being a proper power, right?
Yes, exactly. Yeah. And which in turn is the same thing as having elements of finite order, having torsion. Yeah. Okay. So main results. So main result is that in fact Lauder and Wilton's conjecture is true. So that 2 free one-related groups are hyperbolic, but moreover they are virtually special. So I won't define what this is, but yeah, essentially it's to do with cube complexes, and yeah, you can define what a special cube complex is, and yeah, a special group is a fundamental group of a special cube complex. But what this does get you, so if you're virtually special, then you get residual finiteness. So this is one corollary of the main theorem. So 2 free one-related groups are residually finite. Another corollary is that, well, if you're a 2 free one-related group, then every finitely generated subgroup is again hyperbolic. So not only are you hyperbolic, but you also get this sort of is inherited by subgroups, by finitely generated subgroups. This follows from this plus a result of Gersten, which says that 2-dimensional groups with cohomological dimension 2 have all their finitely presented subgroups hyperbolic. So added with coherence, this gets you that every finitely generated subgroup of such groups are hyperbolic.
Sorry, could you say it again? I thought the result of Gersten required the ambient group to be hyperbolic, no?
Sorry, yes, you're right. Thank you for pointing that out.
So how exactly are you applying it here? So you know that the group itself is hyperbolic.
Yeah, we know that the group itself is hyperbolic.
Oh, sorry, this is a part of
for this result. Yes, sorry. I'll repeat that because yeah, I missed a key hypothesis. So Gersten proved that groups of cohomological dimension 2 that are hyperbolic have all their finitely presented subgroups hyperbolic. So yeah, that plus coherence plus this result gets you that every finitely generated subgroup of such one-related groups are hyperbolic. Okay. And I want to talk about one more application, that is to pair-free one-related groups. So these groups were introduced by Baumslag in 68. So what are they? Well, they're groups which are residually nilpotent. So this essentially means that every element in your group can be sort of distinguished from the trivial elements in their nilpotent quotients. And secondly, that there exists some free group F such that all the these gamma n are well defined to be what G, just these guys inductively, right? And G G1 is just G. So all these quotients are isomorphic. So essentially it means that all your nilpotent quotients are the same as some free group. So yeah, if you want to distinguish your group G from a free group by just looking at its nilpotent quotients, you won't be able to because they're all the same. And well, these groups were introduced by Baumslag as a sort of well, let's say this. So Magnus proved a result which says that a n plus r generated group with, sorry, an n plus a group with presentation with n plus r generators and r relations that is generated by n elements must be free. So he proved this result, I think, in the 30s, and I think at some point in the proof he uses some nilpotent quotients, and I think there was some question floating around whether sort of there was some converse to this result, and Baumslag came along and said no, that's not possible because we have all these groups which are para-free but not actually free. Okay, and it turns out also within the class of one-related groups, there are many para-free one-related groups. So these are just two simple examples, and I gave a family of examples earlier as well. So these groups, which seem, very sort of similar to one-related groups, have sort of seem to be well. The isomorphism problem for one-related groups is very difficult. It's been wide open since one-related groups were studied, and there's no real progress, I guess, other than for particular families. And I think that there was a lot of work trying to distinguish para-free one-related groups from each other, and this sort of led Baumslag to ask the question whether the isomorphism problem is decidable for one-relator para-free groups. And luckily, Baumslag proved this result, which sort of tells us that para-free groups are two-free, and therefore that a para-free one-relator group must be two-free. Therefore, coupled with my result, we can say that para-free one-related groups are hyperbolic, virtually special, and thus the isomorphism problem is decidable by the solution of the isomorphism problem for hyperbolic groups. I imagine this is not sort of the solution which Baumslag would have wanted, but it's a solution to the isomorphism problem for these groups. Okay, so next slide is completing some of the picture of this table. So we have, here we go, this one and this one, which have been filled in, and this is still wide open. I'm not really sure whether I would have wanted this to be true, but since making this table, it just seems quite nice to have all no's in this two-column. I would really sort of make the one-related groups with primitivity rank 2 seem very mysterious. But I have no idea about this. If anyone does, then please let me know so I can complete the table. Okay, so I think, half an hour. Great. I'm halfway through, and I think this is exactly where I wanted to be. So now the next part of the talk is going to be sort of talking about how this result is proved. So this is going to be building on work of Magnus and Danny Wise on some hierarchies for one-related groups, and then we're going to put it together with some stuff of Lauder and Wilton on negative immersions. So I'm going to be working, instead of with presentations of groups, I'm going to be working with one-related complexes. So these are simply combinatorial two complexes with, one skeleton, so some graph gamma, and we have a single two-cell, and the attaching map is an immersion. This squiggly arrow means an immersion. So in terms of one-related groups, well, you can think of a presentation complex of a one-related group, but when the word is cyclically reduced. Okay, this is just to simplify certain things, but yeah, I guess it's not so important that it's immersed. Okay, so first tool is essentially the Magnus hierarchy. So in 1930, Magnus proved the Freiheitssatz, which essentially tells you that given a one-related group, every proper subset of generators or in your presentation, which are mentioned in your relator, this subset generates a free group. And to prove this result, he came up with this hierarchy, which is now known as the Magnus hierarchy. Using this hierarchy, he also proved that the word problem is solvable for one-related groups, and several other pretty nice results. So he of course came up with this hierarchy before HN extensions existed. But then in 1967, Moldovansky noticed that this hierarchy could be essentially reformulated and perhaps streamlined in terms of HN extensions. And then Masters in 2006 also gave an extra simplification. So in the original hierarchy, you sort of essentially split as a HN extension over another one-related group, and then you pass to an overgroup, and then you split, overgroup, split, etc., until you come down to something we know and understand. And Masters came along and said, okay, we don't really need to pass to an overgroup. We can just split, split, split. And the version I'll be talking about today, which I needed to use for my results, is in terms of one-related complexes. So given a one-related complex X, there's a finite sequence of immersions of one-related complexes into xn blah blah up to x, such that each xi splits as a HN extension over the previous xi plus 1, and this psi I identifies two subgroups which are sort of Magnus, correspond to Magnus subcomplexes. So this essentially means just that you are a subcomplex which does not support the attaching map of the single two cell. And then by the Freiheitssatz, that means you generate a free group. So this is and then of course this wouldn't be useful if we didn't sort of terminate at something that we know. So at the bottom we put we have a one-related complex which splits as a free product of cyclic groups. So really this will be, it'll be a free group, free product with a finite cyclic group, or with it will just be a free group. And just a word about these maps. Where do they come from? Well, essentially for each one-related complex, what do? We pick some infinite cyclic cover, KY, and then this x1 will be a subcomplex of this cyclic cover. And then we pick another cyclic cover, take a subcomplex of that, etc., etc., etc. And then all that you need to show is that these subcomplexes induce these splittings, and that's that this sort of terminates in the end. And so I'll call this sort of hierarchy, or this sequence of immersions, together with these identifications, I'll call this a one-relator hierarchy. Okay. So hierarchies of one-relator groups. Well, let's define first some type of hierarchy, which is defined by Danny Wise. Now, I've specialized this definition to one-relator groups. The usual definition is more general than this, but so a one-relator hierarchy is called a quasi-convex one-relator hierarchy if the edge groups of the HN extensions are all quasi-symmetrically embedded in the HN extension for all I strictly less than n. So remember that these AIs are the subgroups which are identified which are Magnus subcomplexes of xi plus 1. I forgot to mention, actually, this identification is induced by the deck group action on Y. So just have some translation, and that's what this AI plus identification with AI with BI plus 1. Okay. So Danny Wise introduced these hierarchies, quasi-convex hierarchies, and he showed that if we have a one-related complex, or one-related group anyway, which has torsion, then every one-related hierarchy for X is quasi-convex one-related hierarchy. Then using a lot of machinery which he developed, he showed, okay, all these hierarchies are quasi-convex. We know that the one-related group with torsion is hyperbolic. So using these hierarchies, he could show that such groups must be virtually special and therefore residually finite. And that's how we resolve Baumschlag's conjecture on residual finiteness for one-related groups with torsion. Okay, so yeah, maybe yeah. So you should think now that maybe we're going to aim for something like this for certain one-related groups, and you'd be right. But in order to get there, I need to define a different type of hierarchy. So this definition may be a little bit technical, so bear with me. I'll try and draw a picture maybe which might help. So take a group H and we take some isomorphism between subgroups of H. So yeah, you should think of, well, what are we going to do? We're going to take some H-n extension of H over psi. Then we inductively define these sets of conjugacy classes. Now these conjugacy classes are in H, not in this H-n extension. So A0 is simply H itself. A1 is B. Then AI plus 1 is defined, well, you take all the previous AIs and we intersect it with A. And then we take the image and the psi, and we just consider the conjugacy class. So two conjugate subgroups are the same. Then we define this AI bar to be the subset of conjugacy classes of non-cyclic elements of AI psi. So yes, what was I going to do? So I'm going to draw a picture. So we should think, okay, we're taking a H-n extension over psi. So what do we have? We have a Basset tree for this H-n extension. So I'm going to just draw a tree, and then it will be clear in a minute why I'm drawing this tree. So, okay, we have this tree, and then we have this orientation, which is induced by, well, induced by this isomorphism. So let's just draw how many, let's draw at least 3. Okay, just to get the picture. So we have things coming in, we have things coming out, we have, yeah, anything. So you should think that these sort of conjugacy classes are going to represent some sort of stabilizer subgroups of this Basset tree. I think I've drawn enough. Okay, so this is my crude drawing of a Basset tree. So here we're going to say this vertex is stabilized by H. Okay, each vertex is stabilized by some conjugate of H. But let's just say this one is stabilized by H. Then this edge here is stabilized by B, or some conjugate of B. Let's say this one's B, and this one's stabilized by A. Okay, so I'm going to highlight this edge here and this edge here, okay, because B is in our set A1, and all the conjugates of B, well, are also in there. So what we're saying is that all the conjugacy classes of all the edges leading into H are in this set. Okay, then let's look at 2. So this is A1, A0 is this guy. A2 will be, well, we look at all the segments of length 2 leading into H, okay, and it's respecting this orientation. Okay, and all the guys in A2 are going to be conjugacy classes of subgroups which stabilize segments of length 2 leading into H. And then, okay, same with A3, A4, etc. That's what these guys are. And we're forgetting about all these edges which, you know, go different directions or have different orientations. We only care about this subtree which is leading right directly into H. And then as you take bigger and bigger I, these AIs are just stabilizers of longer and longer segments leading into H. Okay, so that's what the AI sets are. And then we'll be interested in the stable number of this isomorphism. So what's that? It's the essentially it's the number k plus 1, where k is the largest number such that AK is non-trivial. So you should think of this psi as essentially the first number such that this set becomes just conjugate classes of cyclic groups. Or in terms of this tree, you should think of the stable number I being the first I such that all segments of length I or greater are stabilized by subgroups of rank at most 1. So it could be cyclic, could be trivial. Okay, and then your stable number is infinite if for every I there exists some segments of length I leading into H which has non-cyclic, non-trivial stabilizer. Okay, so hopefully this description was clear. If not, please stop me and complain. So it should be clear what I'm going to do now. So we have a stable number. So we have a hierarchy of one-related complexes, and we say it's stable if these identifying isomorphisms have finite stable numbers. Yeah, maybe another way to think of this is sort of, it sort of seems a bit like acylindricity, but only a specific subtree, and we don't mind having cyclic stabilizers. Okay, well, these a priori, these sort of AI sets, maybe, we don't really know anything about them. They could have loads and loads of conjugate classes of subgroups. It might really not help us much. But for one-related groups, we have that these we take these AIs and we sum over the reduced rank. This is reduced rank. So what rank of A? Reduced rank of A is equal to max of rank A and 0. So the sum of the reduced ranks of all these guys in AN is bounded above by the reduced rank of the edge group A. Okay, so the sort of the ranks can't really expand. We have to have this sort of global upper bound on these ranks. And moreover, there's actually an algorithm that, given as input some integer and one-related splitting, computes generating sets for some conjugate class representatives for each element in AN psi.
So sorry, a couple of questions and comments. I think you're missing a -1 there in the definition of reduced rank, right?
Oh, yes, yeah. Thank you.
And I wanted to check. So this inequality, right? That this sum is less than or equal than the reduced rank of A. So it applies in what circumstance? So what are the assumptions about A and AN? So this is.
So the assumptions are only that these sort of splittings come from the hierarchy, from a one-related hierarchy. So
from some one-related hierarchy or stable hierarchy, or
just any one-related hierarchy.
Any one-related hierarchy.
Yeah, for any one-related hierarchy, we have this inequality. Yeah. So and by one-related hierarchy, I just mean something which comes from this. So you can think of just the Magnus hierarchy, or you can think of take a cyclic cover and you take some subcomplex, a one-related subcomplex, and then you get these sort of splittings induced by that. Yeah, but yeah, I guess I haven't explicitly said exactly what this is, but yeah, if you know the Magnus hierarchy, just think Magnus hierarchy, the splittings which come from the Magnus hierarchy. So yeah, so we have this upper bound, and moreover, we can compute these generating sets. So we have some way of sort of verifying if a splitting of a one-related group is stable, or if or rather the sort of Basset tree has this sort of behavior. And I mean, this is pretty particular to the case of one-related groups, and I guess these sort of splittings. So okay, what are we going to do with this? Well, first let's go through just a simple example. I'll explain later why I chose this example if it's not clear. Well, it won't be clear, but I'll explain later why. So we take this one-related group, okay, then we get a one-related splitting of this one-related group, which looks something like this. So this group splits over, it was one-related group with 3 generators and this relation here, and the identifying isomorphism maps X to Y and Y to Z. Then we can compute these stable numbers. So, okay, we can see that here Y is equal to Z to the minus 2, X squared, Z to the minus 2. So this is like a useless generator. So essentially this group is a free group on 2 generators. So if we have a free group on 2 generators, we know how to compute intersections of subgroups. So all the computations to here become quite straightforward. I won't go into detail about them, but yeah, if you using this relation, this computation is not so bad. For one-related groups, in general it's a little bit more involved because we're not dealing with the free group, but it also can be done algorithmically. So anyway, these are the sets here, and A3 is empty, and therefore this stable number is equal to 3, and this hierarchy is stable. So yeah, there's a hierarchy of length 1. Okay. So okay, we mentioned quasi-convex hierarchies, and we mentioned stable hierarchies. So how do these two concepts connect? So given a one-related complex X and any one-related hierarchy for X, then we have the following equivalence between hierarchies. So one is a quasi-convex hierarchy, and the fundamental group of X is hyperbolic. This is equivalent to this being an acylindrical hierarchy. And what I mean by this is that the fundamental group of X, I, acts acylindrically on the Basset tree for the splitting xi plus 1. Acts acylindrically on the Basset tree for the splitting. So at each step. And this is in turn equivalent to this being a stable hierarchy and the fundamental group of X containing no bounce-like Solitar subgroups. Okay, so let's see, what was I going to say here? Okay, so yeah, so this gives you an equivalence between quasi-convex hierarchies, hyperbolicity, and stable hierarchy in the bounce-like Solitar subgroups. And okay, this condition is quite difficult to check. I mean, it's not clear really how you would go about checking this in general, but I've mentioned that having a stable hierarchy is some sort of algorithmically checkable property for one-related groups. So if we want to determine if a one-related group has such a hierarchy, then we might want to be looking here. But I've said stuff about this, but I haven't said anything about bounce-like Solitar subgroups. Now this is a little bit more tricky, but it turns out that we can actually decide if a one-related complex has a stable hierarchy. We can decide if fundamental group of X contains a bounce-like Solitar subgroup. This does depend quite a bit on having a stable hierarchy. So in general, without having stable hierarchy, yeah, it's not clear how one would proceed here. So I have 10 more minutes, but I'll just give a flavor of this algorithm before moving on to the last section. So yeah, perhaps, okay. So the idea is essentially to every one-related splitting, which appears in the hierarchy, we associate a graph of groups called the graph of cyclic stabilizers. So each vertex group is going to be a cyclic group, and if the stable number is finite, then this graph itself is going to be finite. We can compute this graph to sort of bigger and bigger, we can compute a larger and larger subsets of this graph, and because if it's finite, we can compute the whole thing. Then you can prove that if the fundamental group X contains a bounce-like solid task subgroup, which is not conjugate into this vertex group, then this is sort of equivalent to there being some sort of obvious one which appears in this graph of cyclic groups. I'm not going to say exactly what this means, but I do have a picture in the next page, which hopefully should explain somewhat. So back to our example. So we had this group and it splits like this, right? And the graph of cyclic stabilizers is this. So we have on top, we have groups in one cyclic groups in one vertex, one edge group. So that's A. And then below we've got cyclic groups in the other edge group. So that's B. So psi identifies A with B. And then we have these edges connecting, and the labels here are sort of the conjugating elements. So Y is conjugate by 1 to Y, and X is conjugate by 1 to this, because, X squared, sorry. This is the index here. So X squared is conjugate to this word. You can sort of see that directly in the relator. And here there are no obvious bounce-like solid task subgroups, because, well, this collapses down here, and collapses down here, and that collapses down here. And then what we're left with is a group generated by X and Z squared by Z squared. But this, well, this is just cyclic. So this is not a bounce-like solid task subgroup. We've not found anything. And so it follows that the group we started off with is hyperbolic and has a quasi-convex hierarchy. So yeah, the reason, I promised that I was going to say why I chose this group here. Well, okay, Cash and Hoffman, what did they do? They came up with they have a database of one-related groups up to relator length 17, and by experimental work they proved that one-related groups, so one-relator groups is primitivity rank greater than or equal to 3, one-related groups with primitivity rank greater than or equal to 3, and length of W less than or equal to 17 are hyperbolic. So they experimentally verified Lauder and Wilton's conjecture up to length 17. But of course, they had lots of two-generator one-related groups in their database as well. And if you are not hyperbolic, then the algorithm they use cannot sort of tell you that it's not hyperbolic, because the algorithm they use is a partial algorithm. This is the only algorithm that we know to sort of determine hyperbolicity, because hyperbolicity is undecidable in general. So this is one example I took from their database, which hyperbolicity could not be established. So that's why I chosen this example, and also because it gives the graph is mildly is not trivial. Okay, so I think I have 5 minutes left, but that should be fine. This last section is pretty short. So the last thing I wanted to talk about was negative immersions for one-relator complexes. So this definition, okay, let me say the definition first. So a finite two complex X has negative immersions if for every immersion of finite two complexes Y into X, either the Euler characteristic of Y is strictly negative, or Y Nielsen reduces to a graph. Now, this just essentially means that your homotopy equivalent to a graph, but it's a bit stronger. I mean, I guess it sort of corresponds to doing Nielsen moves on your relator to sort of trivialize the relator. So yeah, it's like you take your attaching maps and you can trivialize these attaching maps by doing some basic moves, basically. So that's the property of negative immersions. This was, I guess this was originally, well, non-positive immersions was originally introduced by Danny Wise around 20 years ago, and this particular definition is due to Lauder and Wilton, but I think Danny Wise has his own version of negative immersions, which is slightly different to this one. So I just want to emphasize that it's not exactly the same definition. So why am I introducing this this definition? Well, for one-related complexes, there's this really nice algebraic characterization due to Lauder and Wilton. So they show that one-related complex X has negative immersions if and only if its fundamental group is 2 free. So this sort of gives you an algorithm to decide whether your one-related complex has negative immersions. From this sort of property, which seems, well, impossible to check, you have so many possible immersions into this complex, you have something which you can actually decide in the context of one-related groups. This is because we can compute primitivity rank of words in free groups. Okay, so the final thing I wanted to say here is that we can use the property of negative immersions to show that every one-related hierarchy for a one-related complex with negative immersions is stable. And so using this result, well, we have, okay, take a one-related complex with negative immersions, you're 2 free by Lauder and Wilton's result, so you contain no bound-stack solitar subgroups. You have a stable hierarchy. Therefore, by the hierarchy equivalence theorem, which I mentioned earlier, the fundamental group must be hyperbolic, and all your hierarchies are quasi-convex. Therefore, finally, by work of Danny Wise, the fundamental group of X is virtually special and therefore residually finite. Okay, so that's what I wanted to talk to you about today. So thank you very much.
All right, thank you. Okay, so now if there are any questions to the speaker, you're welcome to ask them. So I actually had a bunch of questions. So this condition for one related group is the defining relation W to be 2 free. Is it actually equivalent to saying that W has primitivity rank greater than or equal than 3? You know, or I mean, one way I can see so, but the other way. So is it equivalent, or is there only implication one way?
Yes, yeah, it's equivalent because I mean, if you have primitivity rank.
If you have primitivity rank at least 3, then it's Lauder Wilton theorem, right? But what if you start with the assumption that the group is 2 free? You know, why does W have to have a primitivity rank at least 3? Why can't it be 2?
Well, so if you have primitivity rank 2, then there's some subgroup K in F with rank of K equal to 2 and K, and W in K in primitive, yes. Right? And then Lauder and Wilton show that K quotiented by this guy, this word W, injects into. Oh,
I see. So they also show that. Okay.
So then, yeah. So then this is actually a non-free 2-generator group.
I see.
Yeah.
Okay. Another question I had was about this hierarchy equivalence theorem. Could you scroll back to it? In order to get condition 1, the first condition from either the second or the third, I don't know, you know, how you prove this equivalences, but are you using the combination theorem, or how do you get that pi1 of X is hyperbolic, let's say, from the third condition?
From the third condition, so
or even from the second, you know, I want to understand what technical tool is being used to conclude hyperbolicity.
So, yeah, one technical tool is a theorem of yours actually. So from the combination theorem, if your vertex groups are hyperbolic and you act acylindrically on the Basset tree, then by the classical combination theorem, you are hyperbolic, but then I think by your result, you also get that your vertex group is also quasi-convex. And therefore, yeah, then the edge groups also are quasi-convex. So that sort of gives part of this equivalence here. And then, yeah, the other equivalence, so you can prove if you're stable, then all the stabilizers of big enough segments are going to be either cyclic or trivial. And then, yeah, the main argument is essentially saying if all these stabilizers are cyclic, then somehow you can find some cyclic group which is conjugated to another cyclic group, and that gives you a bounce-like solitar subgroup. So yeah, it's this, and then these two.
Okay, very good. Thank you.
I have a question. Actually, first of all, thank you for the talk, and I think it's a strong result. And my question is, so you have a kind of procedure. So you have this one-relator, your one-relator group, and you produce a subgroup of finite index and a special cube complex on which such that this group is a fundamental group of this complex. So is this procedure effective? I think it should be so.
To find the cube complex, you mean? Yeah. I don't think so. So the way I prove that these one-related groups are virtually special is it appeals to this Danny-Wise theorem that if you're hyperbolic and you have a quasi-convex hierarchy,
okay,
then you're virtually special.
But I think that there is a cheating. You can do some kind of a naive general enumeration procedure. You can start enumerating special complexes and look for sort of maps going back and forth. And I think if you know that the group is virtually special, you can eventually find the complex in the subgroup of finite index, just by some sort of stupid general enumeration.
Well, I was thinking about like a real procedure. So
right. Okay, if you want something that has any hope of actually running in real time, then no.
Yeah, not that I can think of. Yeah.
All right. Any other questions? Okay, let us thank Marco again. Thank you.
Thank you again for inviting me.